Let's turn it off for a second.
Oh, welcome to the Mechanical and Aerospace Engineering Department annual Dr. Carl Zorowski Distinguished Lecture Series. Uh, we do it every year, and Dr. Zorowski legacy is the reason why we continue to do this to honor his memory. The lecture series itself is dedicated to, as I said, to late MAE department head, Dr. Zorowski. He was also professor emeritus, and he was in the college over 60 years. So long career. Dr. Zorowski passed away April 5th, 2021. Lucky I had an opportunity to meet him at least a few times before that. It was wonderful. I spent a lot of time with him. A great visionary. He said a lot of great stories to me about how his life at NC State was, and he shared details about his car racing ventures. I think his daughter was a pit crew, who was also a graduate of MAE. So a lot of interesting stories, and he really was passionate about bringing people who could bring forth a legacy to how we shape the department. And one of the passions he had was mechanical design. And for many of the students here who might not know, the senior design format with the industry funding was started by Dr. Zorowski in this department. So that's the legacy he's got. And all that machine shop you're thinking about using or are using right now are part of his legacy. So, I do feel like that lab should be named Dr. Zorowski Lab. Maybe we'll figure out a way to do that in the future. Dr. Zorowski also served as a department head and also the college associate dean. And he also created this Integrated Manufacturing Systems Engineering Institute. He worked in many areas, including as consultant to industry. And he also started one of our study abroad programs, which no longer exists, but it was very popular in the 2000s. That is after he retired. So technically, he did something for the college even after he retired. He was in fact, I think the first year I was here, 2017, I think he was still teaching a class, and then after that he quit. But I got to meet him a few times after that, and as we talked about setting up this distinguished lecture series. So it's my pleasure, actually, to introduce our speaker for our lecture this year, Dr. Charles Jenckes, who is a third-generation engineer from his family, and he has a Bachelor of Science degree from Drexel. Then he got his Master's of Science and PhD from NC State MAE department. He's also studied at University of Wisconsin-Madison and MIT, and his primary areas of research concentration, I would say, I'm going to frame that differently, include fluid dynamics, thermodynamics, combustion, and vehicle dynamics. In addition to this research thing, he also has 30 years of professional motorsport experience. And as you know, Dr. Zorowski was passionate about motorsports, so it was automatically easy to connect Dr. Jenckes, who also knows Dr. Jenckes knows Dr. Zorowski personally. So there's this huge connection there. And after his 30 years, you'll see that during his talk. In fact, we had a great dinner last night. He talked about his motorsports experience. A lot of stuff to share. He has contributed to championships in several motorsports events. They're all listed there. He has also done work for Ferrari, Haas, and Williams F1, which is going to be very intriguing to listen to. He's also was the aerodynamicist for the world's fastest piston-powered vehicle, the Speed Demon 2, which set a record of 481.6 miles per hour at the Bonneville Flats. So he currently teaches at Purdue University's Mechanical Engineering Department in the College of Engineering on the campus at Indianapolis. He has an active consulting business for motorsport clients. Dr. Jenckes is also working as part of a consortium that will be supporting DARPA's cyber physical system executing in real time, which is called Cypher Forge project. So please welcome Dr. Charles Jenckes.
Thank you. Thank you, Dr. Arquette. Well, thank you for having me back. It's wonderful to visit NC State again, and go Wolfpack. I'm going to spend a few minutes remembering Dr. Zorowski, do an introduction, cover a little history, and then I'll spend a few minutes discussing motorsport aerodynamic development, and I'll finish up with some applications of artificial intelligence and machine learning in motorsports, what I see the future's going to be, and then I'll make a few concluding remarks. First, I want to thank Dr. Zorowski. Dr. Zorowski taught many classes. Dr. Arquette had outlined some of his career achievements. He was a department head at MAE, and he came from the Carnegie Institute of Technology, which is now Carnegie Mellon, excellent engineering school, but found his home here. And as Dr. Arquette said, he was an avid motorsports enthusiast, but he was also very passionate about engineering and engineering education, and he was very innovative. As Dr. Arquette said, I'm not sure he started the study abroad program, but he certainly made it very strong. And he initiated several programs, including a study abroad in China. I have a little clip here of of Dr. Zorowski, one of his lectures that I was fortunate enough to take.
Good morning. This is session number 13 of MA 495-589, Mechanical Design Engineering. Since this is Tuesday, we want to start off with a little brain game again. Like to have our little brain games every morning. Okay. Tuesday mornings. This was in last Sunday's paper, so you can get a head start on this. If you get the N and O on Sunday, you can get these. All right, what do we got?
Stain on the
Stain.
button.
Straw.
Dog's tail.
Dog tail.
Hat.
Hat.
Button.
Button.
The straw.
6-1.
Okay, so you can see Dr. Zorowski was a great professor, and he always started his lectures with this. Well, once a week he would start with this this brain game, and so this was the kind of educational format that he really enjoyed and pioneered. This is a picture of Dr. Zorowski at the Caterpillar facility in Suzhou, China. So you can see that he was instrumental in some of these educational formats. He also had many distinguished students, including one right here, which you may know as Dr. Aishin. So Dr. Zorowski's class was very popular. It was generally full, and he taught engineering from first principles. So I'm just going to give you a taste of one of his example problems, which was very practical, but what he was excellent at was tying the practical and the theoretical. So this was a little transmission shift example, and what he asked, are these shift points the same, and how would you find out? And he goes through a pretty good example and has a great conclusion. But that's just an example of his teaching style. I think it's very, very excellent to tie the practical to the theoretical. I think that's why senior design is so important. You spend the first 3 years of your educational career covering all of the theory. And then in senior design, you have to tie that into something practical. And this really is the springboard to help you in your industry career. So I'm going to talk a little bit today about motorsports. Motorsports is interesting. It lies at the intersection of human performance, engineering, and entertainment. From the earliest days of the automobile, motorsports is defined as state-of-the-art in automotive technology. Today, Formula One is second only to European football in worldwide viewership. And really, the engineering technology in F1 is unrivaled. It's equivalent to the defense technology that's there today in aerospace. Not necessarily the same depth, but what is unrivaled by F1 engineering is the speed at which they can make design changes that are effective and have them implemented. NASCAR, in addition, is among the most watched events in the US, and certainly in North Carolina, there's a strong motorsports presence with all of the teams in the Charlotte area. So I'm going to cover a little history. This is a Formula Ford circa mid-70s, and this is how I started my career working as a mechanic. I'd often do car maintenance and things like gear ratio changes at the track. This was all before I could drive. This is a Formula Atlantic car. Formula Atlantic was a feeder series. It was really like Indy Lights, but many Formula One drivers and top IndyCar drivers came out of this series in the 70s. Names like Villeneuve and Rahal were key. One thing you can see in this car, it was already in the aerodynamic era, but I want you to notice how the car is rolled and how the front splitter is not necessarily parallel to the track surface, which is something we would have liked to have seen. So while we had the aerodynamic tools, we were still getting that combination of the aerodynamic performance and the vehicle dynamic performance to optimize the aerodynamic potential. I worked in the early days of IMSA. This is a cover for a magazine in the 70s. The middle car there, the blue and yellow car, was a car owned by Al Holbert and Holbert Racing. That was the team that I worked for. You can see also the white Martini car, number 2, on the bottom of the picture. That was a Porsche factory car. So back in the day, to be on the cover of a premier magazine with the Porsche factory was a significant honor. Al Holbert was also an engineer. He was a driver, a top driver, a champion, competed in many different series, but he was also a practicing engineer, and he went to Lehigh University and got an undergraduate engineering degree. Interestingly enough, he came from a family of motorsports. His father, Bob Holbert, was a factory driver for Carroll Shelby of the Ford versus Ferrari fame. So the family was steeped in motorsports. To work for Holbert Racing at the time was quite significant. They had won Trans Am championships and 2 back-to-back IMSA championships in 76 and 77. That's a picture of Al as I knew him, and this was the 76 car. It was IMSA in the day was a sedan-based racing series, somewhat like GT3, but much more open. You'll note this car did not have any wings or splitters in the early days. What IMSA did, though, is they allowed 2-frame bespoke chassis to compete with cars like the Porsche 934 and BMW CSLs of the day. So it was factory involvement. In fact, Porsche, Chevy, BMW, and other OEMs directly participated. But the key thing I want you to see here is the limited aerodynamics of the car. It was interesting, in 1977, they started the season with the 76 car, even though the regulations had opened up for aerodynamics, which I'll cover in a second. But this slide shows the 24 hours of Daytona in 1976. Now, Al, as I said, was the team leader and driver, and also a practicing engineer. So he, in this period of time, the high speeds at Daytona required the cars to run a pretty significant engine speed. And the pushrod V8s of the day, even the racing engines, weren't really capable of the sustained RPM needed to be competitive on the Daytona banking. And for the 24-hour race, it was a real challenge. And Al knew that to really be competitive, you needed to run these speeds. This car actually qualified 8th in an international field, and it was the highest placing American car, or American team. And what happened was Al knew that it wasn't likely that the valve train in this particular engine was going to survive for the 24 hours. But the 24-hour race was very important for the championship. It had, I think, double points at the time. So it was really desirable to finish the race and get good points. So Al, in the fall, decided that what would happen is we would do an engine change during the 24-hour race, so to keep the car competitive. So we worked all winter to prepare the chassis so that the engine could be changed very quickly. And actually, the engine was able to be changed in 20 minutes during this event. I actually worked underneath the car, and there are pictures somewhere of me getting up soaked in oil after having changed an oil line. So this was quite an interesting engineering exercise to realize the limits of the capability of the powertrain and then adapt that to the racing environment. This is the 77 car, and you'll notice that there's a splitter and a dual element rear wing. The team worked with GM Motorsports during this time to develop this aerodynamic package. You'll also notice that this car is heavily loaded in cornering, and you can see that the splitter is much more kind of even with the ground, parallel to the bottom of the splitter is parallel to the ground. That's some of the advances that had been made in a short period of time to understand the coupling of vehicle dynamics and aerodynamics. This car is a Porsche that was raced in the same era. It's a 934. It was a production-based car. It started life as a production-based car and was turned into a motorsports vehicle. Al Holbert, the family owned a Porsche dealership. His father had started it in the 50s, and so they were very well connected with Porsche. And in fact, Al later went on to be the head of Porsche Motorsports in the United States after his driving career. Unfortunately, Al passed away in an airplane incident. Nevertheless, Porsche was a big part of Holbert Racing, and in fact, this car was raced by my supervisor at the time, and I was race engineer for this in an early age. I then went to university to study at Drexel, and my co-ops were in this wind tunnel. This wind tunnel is outside of Philadelphia, near Drexel, and it's the largest moving belt ground plane wind tunnel in the country. It has a 20 by 20 test section, and as I said, having a moving ground plane in the 60s and 70s was really innovative. I've spent a lot of time in wind tunnels over the years, but this was certainly a very advanced wind tunnel. All of Boeing's aircraft and helicopters, anything that sees flight, goes through this tunnel for ground effect investigations before it proceeds on. This tunnel was built in 1968 and is still in service today. During my undergraduate years, I was called back by Holberts to be the race engineer on this vehicle. It was a D production car in SCCA. Now SCCA today isn't very strong, but in the 70s and 80s, factories, OEMs, participated in SCCA racing, and Porsche, BMW, the British manufacturers at the time, all had factory efforts, and Porsche was introducing a new car called the 924, which later became the 944, a pretty famous line, but they wanted to race it, and then my supervisor, Doc Bundy, was going to be the driver for this. They called me back from uni to be the race engineer on this car. We had to do just a couple of races, so it wasn't too tough on my academic schedule. And we qualified for the runoffs, and back in this day, you had to qualify for the runoff championships. It was at Road Atlanta, and Doc drove an amazing race, passing the Triumph TR6 on the last lap to win the runoff. So really excellent experience, and the TR6 had much more power than the Porsche did. It was a 6-cylinder British car. The Porsche only had a 4-cylinder engine, so power was, in the strength of the British car. But we had balanced the Porsche very well, and while it wasn't very aerodynamic in this era, we did a great job with setting the car up for Doc so he could drive it, and he did a great job. I'm still friends with Doc to this day. When he's still racing, he races a Lotus and Vintage, and whenever he runs, I often go in and do the race engineering work for him. So after uni, I went to work in GM Motorsports and GM and suppliers for GM Motorsports and production-based racing. The Camaro Firebird, Corvette, these kinds of cars were fully supported by GM at the time. A lot of investment into these kind of vehicles. I also made my first trip to the Bonneville Salt Flats during this time. This is a picture of a production-bodied Firebird that had a NASCAR engine installed it and went 225 miles an hour in 1991. So that was not only a record for this body style or production-bodied cars, but it was also an FIA record at the time for the engine displacement. I then went down to NASCAR. I started working for Joe Gibbs Racing in the late 90s, and NASCAR was much different than it is today. When I went to NASCAR, there were very few engineers, and we did everything. We went, certainly did the wind tunnel testing at the time, but we had to put data systems on cars, do race engineering, whatever was needed. It was very uncommon for teams actually to have engineers. Gibbs was was and is one of the leaders in engineering in NASCAR, and we only, but at the time when I got hired in, we only had 3 or 4 engineers on staff. Today they probably have hundreds. I was recruited by Dale Earnhardt to go to DEI while I was at Gibbs, and after my contract was up, I went there. And unfortunately, while I had been hired by Dale Earnhardt, one of the reasons I went there is he had a vision to create a center for GM Motorsports in Kannapolis on the DEI facility. His vision was to build a wind tunnel, have a test track, and really do what GM Motorsports is doing today in Concord. He was going to build a complete facility there to service all of GM's racing's needs. And he was planning on retiring in a year, the year after he was killed at Daytona, and he was going to then lead the Corvette effort to go to Le Mans. And at this time, he was driving Corvettes and road racing very successfully, and his idea was then he was going to be the lead driver for the Corvette team to go to Le Mans. Unfortunately, he was killed at Daytona in 2001, and this dream never became reality. In fact, DEI really ceased to exist a few years later. I'm showing this car because this car was driven by Ron Fellows at Watkins Glen. That year, we did a specialty vehicle, often at DEI, although I was mostly working on aerodynamics. I filled in as a race engineer whenever they ran a 3rd or 4th car, and this car was my best finish ever in Cup. We finished 2nd that day to Tony Stewart, but we should have won the race. Of course, there's always should-haves in motorsports, but the qualifying was rained out, and we had to start 43rd. But Ron Fellows drove from 43rd to 2nd, and you know, if qualifying hadn't been rained out and we'd started anywhere near the front of the field, we probably would have had a very successful day. After DEI kind of stopped being Dale Earnhardt Incorporated, Dale Jr. left to go to Hendrick Motorsports, and the family, the children and the owner, Teresa Earnhardt, really had a kind of a falling out, and the company disintegrated. I had a long-term contract at DEI. I had just signed prior to Dale Jr. leaving, so I really couldn't work in NASCAR or IndyCar by contract, so I went to work. I had met a great engineer named Osamu Goto. Goto-san was the head of Honda Formula One in their first foray. You can see that on the left, he's with Alan Prost, and on the right, he's with Ayrton Senna. 2 of the top drivers of their day. Honda was the premier powertrain and factory support for McLaren Racing in Formula One. They won multiple championships. Goto-san was renowned, but typically at Honda, they want the lead engineers to come back into the production car world, and Goto-san wanted to stay in racing, so he left, and he went to Ferrari, and then he created his own consultancy in Montreux, Switzerland. That's the top picture there, an unbelievably beautiful place. I had met Goto-san during my travels, and he offered me a position working for him, and this was my first foray into working for Europe. So I was contracted at first to Aston Martin to help with this Le Mans program, and then I went to work as a contractor at Ferrari, and this is a picture of Ferrari's wind tunnel where I was resident. When I was at Ferrari, it was clear to me that all of the top Formula One aerodynamicists, really to get a job with a team in aerodynamics in Formula One, you had to have a PhD. It was really the ticket to entry. And education is very highly valued in Formula One. So many of the aerodynamicists went to Imperial College in London, which is basically the UK's MIT. And they had great education, great experiences there. And so I realized that if I wanted to continue into Formula One, I needed to get a PhD. And so although I was, in mid-career, that's when I decided to come back to North Carolina and come to NC State and start my academic endeavors here. I often say I went back to school and I got a PhD instead of a Porsche. So while I was finishing up my dissertation, I went to work for Chip Ganassi in NASCAR, and I did a couple of years there while I was writing my dissertation. And we had some very successful times, although the team was woefully underfunded. Chip tended to take all the NASCAR money and funnel it to his passion, which was IndyCar racing, which I'll talk about in a minute. And then during this time, I was recruited to go to Haas F1. So I was the third technical employee hired by Haas. They were looking for some US people, and in 2014, the team was started. During this period, I was still writing my dissertation. I worked to help start the aero calculations group at Haas F1, which was basically CFD, wind tunnel support, aeroelasticity work, and correlation. And I'll talk about that in a little bit. But Haas originally thought they were going to run everything from the US. They built a full Formula One style race shop with a composites lab, all in North Carolina, north of Charlotte. They were going to use the wind shear wind tunnel that Gene Haas owned. And in fact, we spent the summer of 2014 trying to retrofit the tunnel for 60% scale work. And then by the end of the summer, the team principal was someone you may know from Drive to Survive named Gunther Steiner. Gunther was the visionary behind Haas F1. If it weren't for Gunther Steiner, Haas F1 wouldn't exist. That's a fact. And Gunther realized very quickly that we weren't going to be competitive by being based in the US, because all of the support structures were in Europe. So we needed a powertrain supplier. Initially, Mercedes was winning the championships at this time. They were going to use the powertrain from the Mercedes. But Ferrari, there had been a recent rule change, and Ferrari had fallen behind a little bit, and they needed some support. They needed some money from Gene Haas. And so we ended up having a partnership with Ferrari. They were going to supply the powertrain, and we were going to test in their wind tunnel. So the race shop was in Banbury, UK, in the Midlands. And you'll notice now that Cadillac is getting back into Formula One with Andretti. You'll notice that there's a huge facility here in the Charlotte area that's supporting that effort, but the race team, despite the fact that Andretti is based in Indianapolis, the race team's going to be in the UK at Silverstone. It's very, very hard to compete in Formula One with the US base because all of the supply infrastructure is really in Europe. So even today, this is the pattern that's being used. In any case, Haas had offices here in North Carolina next to their Stewart-Haas facility. They had wind shear, but ultimately we ended up testing in Europe and partnering with Dallara to help actually with the construction of the car. And Dallara, you probably know, they're the largest race car manufacturer in the world. They supply 100% of the chassis used in IndyCar. They designed the current generation NASCAR vehicle for NASCAR. They designed and executed the whole design, and I designed pretty much every part of that car except for the transmission, which was supplied by X-Track, and then the body panels, which were supplied by the US OEMs. This was a picture of Ferrari from when I worked there, from my favorite coffee shop across the car park. Ferrari was very full at the time. If you wanted to get a parking spot in this car park, you had to get there very early. So I was living in Parma. I had to drive up there, and I'd get in the car park early and I'd go across the road and get an espresso and wait for the day to start. This is a picture of the wind tunnel. This wind tunnel is one of the finest wind tunnels in the world. The instrumentation in Ferrari's wind tunnel is the best that there is. and the repeatability is really incredible. This is a picture of a wind tunnel model from the first years at Haas. You can see that the blue body panels are all rapid prototype panels. This is a 60% scale car. You'll note that the tires are rubber. You know, the model is fully functioning for suspension. These are very, very intricate models, multi-million-dollar models, and they're really designed as aerodynamic tools. You can see that the front wing has all the furniture on it. Anything that's highly loaded was either metal or metal plated, but generally any of the blue parts were SLA, and the idea was that you could change these parts very quickly. It wasn't uncommon for wind tunnel shifts would be 24 hours. It wasn't uncommon to have several hundred model changes during that time, several hundred parts changes. So to do this very efficiently was key, and obviously in F1 this is something that they do. Typically, a Formula One team spends 2 weeks out of 4 in the wind tunnel, or 50% of the time, and that's regulated, so they can't really run more than that. In Formula One, both wind tunnel time and computational fluids time is regulated, and you have to be very efficient at what you do. This model is now moved to most forms of motorsports, where even in NASCAR, both wind tunnel time and CFD time are limited. This is a picture of a launch day outside of Dallara with the car. I think this was 2017 or 18, and the whole team at Dallara and Haas was there to launch the car. Examples of the cars, and this is some of the cars that we worked on up until 2020. One interesting thing is, if you notice the picture of the rear wing in the lower right-hand corner, that's something that we developed that was pretty unique, and it was designed for one race, Monza, and Monza is a very fast track which requires excellent aerodynamic efficiency and very high speeds. But the reason that wing is three-dimensional in shape is that Formula One has a rule that allows the rear flap to open to reduce drag to help passing. That's called the drag reduction system, or DRS, and that particular shape allowed a greater drag reduction with the flap open, and that was something that was developed in math before we took it to the wind tunnel. I want to show you this. This is between Haas and Williams. I worked at Chip Ganassi Racing on the IndyCar program for a little while, and this is a different type of wind tunnel. This is an actual old railroad tunnel that Ganassi has converted to run in straight line testing. So you'll see that the car there is sitting on a turntable, and there's a turntable at both ends of this tunnel, so the car runs down with a driver in it, turns around, and comes back, and you get 2 passes. And the advantage of this is that it's a race car on the ground, and the tunnel provides shelter from any wind conditions, and it's almost constant temperature. So it has some very good advantages real world, but you can't yaw the car, so you can't see any kind of yaw performance. So, but this was a tool that Ganassi used and still uses today, although it also is limited by rules. It's unique. Now there's a similar old railroad tunnel in the UK that has been converted to this type of activity. After CGR, I went to Williams for a little while and worked on the previous generation car to this, and you know, Williams is a storied team, lots of history, but it was going through some very tumultuous times when I was there. In fact, while I was there, the owner, well, the current owner at the time, Claire Williams, Frank Williams' daughter, ran the team, sold the team, and then also Frank passed away, which was a very traumatic experience for the organization. But Williams is a small team. They were hoping at the time that I joined it that they were going to be purchased by VW Porsche, but that didn't happen. And as a result, there was more chaos, and ultimately, I came back to the U.S. Now I'm going to talk a little bit about an exercise I did while I was at Haas, and this is the Speed Demon car, the Bonneville Salt Flask car. This was the first car that they built, it was very successful, but it had some significant aerodynamic issues. I'm going to show you a little clip here. Now, the driver survived that. The driver at the time is George Petit. He was probably 80 years old when that accident happened. This happened in September of 2014. I was not involved with the team at this time, but they had an aerodynamist from Lockheed that was working with the car. But they obviously had some problems. What happened was there was a crosswind, and the car yawed significantly and ultimately was lost control, and it was not recoverable. This is evidence of that. So I was hired to come in and provide an alternate aerodynamic analysis, and this is some a CFD image that I did at the time, and I want to show you that this is evidence of the strength of computational fluids. What computational fluids does that you can't do easily in the wind tunnel or on the track is it provides great visualization. And in this slide, you can see clearly that the scoop on the top of the car has a separation, and the wake from that scoop is impacting the tail. So the tail, the vertical stabilizer, which helps with the yaw performance, is relatively tall, but you can see that the wake from that scoop separation really shows that only the top portion of that tail was functional. And so through this analysis, the car, they were already in the process of rebuilding the car when I got involved in the program. So it was pretty clear to me what happened and what needed to be done. So we went through and redesigned the car within the constraints that we were given. And this is typical for engineering. You know, you don't always get a clean sheet. You've got to work within the constraints. Now, a couple of key things here. The scoop on the car on the right fed the turbochargers that powered the car. This car made approximately 3,000 horsepower. And one of the things that happened is you could see in that previous CFD image that the air was shearing off the top of that scoop, and the scoop wasn't being particularly effective. So one of the problems they had with this was that the turbine inlets for the turbochargers were not seeing constant pressure. And this was causing some compressor stall, very undesirable for engine performance. So I did the analysis using CFD tools, using the math tools, and I identified the source of the compressor stall, which was the pressure, the active pressure in the duct. And you'll notice that on the Gold car, the holes in the side are actually the inlets for the turbines, and you'll notice the car has kind of hips, and that area is a high pressure area. So I mapped out the pressures, found a high pressure area that was stable, and we used that for the turbine inlets. You'll also know that the top of the car is kind of shaped, so we worked very much on the boundary layer and tried to make sure that the tail saw a strong, clean boundary layer at the base of it, and that it was very effective. So the calculation showed that we had more than doubled the yaw performance of the car, went back and had great success. Bonneville is a kind of an unearthly place. If you ever get there, it's like being on kind of what you might imagine being on the surface of the moon. The road surface is not very smooth. It's very rough. It's like a dirt road, really. So it's very tough. And the mountains in the back, when there are crosswinds, there's gaps in the mountains, and it causes some variability in the incident angles for the wind the car sees. So you have to build a car that's stable, and it can handle the crosswinds, and that was the difference between these two vehicles. The day before the record run, at Bonneville, it's a very old school kind of racing experience. You have to, everybody has to do everything. And on the day before the record run, they had an issue with the calibration, and they hold a piston. You can see it on the left side there. You can see a hole right through it to the connecting rod. Well, this needed to be replaced. So we had to do a piston change at the track. And on the right side, you can see that I'm working on the engine. The engine is sitting on the floor of the trailer, and we did a piston change. Now, you know, whenever you do a piston change, you have to put new rings in. When you have new rings, you want to break the glaze on the surface of the cylinder, so we had to use a ball hone in order to break that glaze, gap the rings, put the piston in. We did all this, and then the next day we went out and set the record. This gives you an idea of, you know, some of the challenges you face. The tires run so fast, and there's so much heat that every time you run the car, there's some delamination. This is safe, but it shows you the stresses, and these tires had to be replaced every run. So the results were that, you know, we set the records the next day in 2020, and the car went 481.6 miles an hour. Gives you an idea of the complexity of the vehicle. The single turbocharged, twin turbocharged engine powered the vehicle. That, after the records were run, the owner of the car and the driver, George Petit, who was in his 80s, wanted to keep racing, but his back really was not capable of it. So he wanted to retire the car and bring up a new driver. So someone that we all knew, Chris Rasky, became the driver of the Speed Demon. George supported the team for a year or so, and then he unfortunately passed away at I think he was 88 when he died. The family allowed the team to run the car for one more year, the gold car, with some smaller engines, and they set more records. But the owner of the team wanted to keep going, and they started a third Speed Demon project. That I was not involved with at all, because they had no money. They didn't even have money for computational time. So we couldn't do, well, I didn't do any work with them when they built the next car. And unfortunately, in August of this year, they had a fatality with Chris driving the car. They had a deflation of the right rear tire at about 300 miles an hour. That deflation was sudden. The car ran over a piece of debris on the track. The tire deflated, and it created a high pressure area in the wheel well, which drove the left front of the car into the salt. When it rebounded, it wanted to sit back on the right rear, but there was no tire to support it, and it lifted the nose, and the car took off. It flew about 18 feet in the air, and unfortunately, when the car hit the salt, the driver sustained about 250 Gs, and of course that's not survivable. This happened at the Salt Flats, which is federally owned, so the accident is being investigated much like a aircraft incident. And because of my experience, they brought me in to do the accident reconstruction. So I can't really talk too much about that because it's active. But I was asked to do a CFD analysis of the car, and there was no surface data on the car, so I had to take a wooden model that they had used, a scale to build prepare for the tooling for the body that they built. I scanned that, rescaled it, and did some CFD work, and identified that the car itself was really okay and stable, but that the issue was clearly the tire, and I went through the data and showed that. So that's all an active investigation. I think the team will be reconstructed after all that settles down, and they'll probably go back. And of course, they've asked me to go ahead and design the next car. So now I'm going to talk a little bit about aerodynamic tools and motorsports. The three tools that we have are wind tunnel testing, computational fluids, and on-track testing. And of course, each one of these tools has a strength and weaknesses, like any tool set does. Now, we think about wind tunnel testing, and we think, well, that's got to be very representative of the real world. But the truth is it's a simulation. The car is stable. It's static. The ground plane moves, maybe, and the wind moves. But in the real world, of course, the ground is fixed, and the air is fixed, and the vehicle moves. So you can see that there are sources of error there. And we have computational fluids. Now, for those of you that have fluids, you know that the Navier-Stokes equations are very complex. They're nonlinear partial differential equations. And the truth is, in order to solve them explicitly, to solve the equations fully, requires an unbelievable amount of computational time. So to do a Formula One or an Indy car and do one case, it might take, with the largest computers, weeks to solve explicitly. So in order to make that more feasible, we use turbulence models to close the equations. Now, I'm not going to go into all that today, but the point is it's an approximation. But it's a good approximation, and it's very helpful. But the point is, this is a simulation too, and it's not exact. And then we have track testing. Well, you think that's the real world. That should be the best. But the truth is, there are always multiple variables at the track. There are crosswinds, temperature changes, tire degradation. All of these factors lead into variables and error sets that are quantifiable and are quite large. And so, in fact, they're larger than the repeatability that you would see in a wind tunnel. So it's only when we look at all three of these tools together that we really get a clear picture, the clearest picture of what's going on. But that's at a small intersection of all of this data. And one of the things this leads to is a field of study called the quantification of uncertainty, which means that we do error analysis on each one of these tools, and we want to look at and understand exactly how much error we have. So a typical motorsports development program for Formula One will start out with CFD. You might take 10 ideas in CFD, and then you might evaluate them, and then you would shrink that down into maybe 3 or 4 ideas you would take to the wind tunnel. You would evaluate those, and then maybe 1 or 2 gets to the track. And this is the typical development process. So again, you'd start with surface design, create CFD cases, run through the wind tunnel, and ultimately get to the track with it. So one of the key things that we have to do is correlate all this data. And this is a standard procedure. You take the track, the wind tunnel, and the CFD data, and you kind of look at them all together to try and understand, to get the clearest picture. And in the wind tunnel, we use very advanced rakes to measure things. We can also use laser Doppler anemometry we can seed the air with small particles, and we can get an idea of what the velocity is at each point, so this helps us validate our CFD models. And now I'm just going to give you a really quick overview of like one type of analysis that you might do in Formula One, and that would be looking at vortical flows on parts. Now this is from currently 2 generations ago in Formula One, so none of this is proprietary, but you might want to look at how these aerodynamic elements interact. And so we have things like turning vanes, and we have a vortex that's created off the front wing, and we have a mid-turning vane, a front-turning vane, a mid-turning vane. So you can see kind of the elaborate geometries that we have here. You can see that one of the things we're doing is we're looking at how these vortical structures interact. And one of the key things is the direction of the rotation of these vortices. So Of course, we wanted to track and understand these. We did create a mathematical algorithm that we used to analyze these structures in CFD, and you can kind of see, you know, at two different planes how the structures change. We identify the locations and centers of the pressures. We understand kind of the radius that they're working under, and then we're able to kind of plot the circulation and the equivalent radius so we can understand, and I'm not going to go through the math, but here's a plot of different geometries and their performance relative to each other. This is the type of analysis that you would do. And then we would track these vertical structures as they go down the long axis of the car, the x-axis. Now I'm going to close up with a few comments about the future. So AI is going to impact every aspect of motorsports team operation. Everything from business, race strategy, engineering, aerodynamics, any part of it. What you're going to find is that even in the business operations, that AI can do the heavy lifting for kind of commonplace tasks that we might have had humans doing in the past. For example, truck routing, okay? I mean, that doesn't seem like a lot, but if you can save dollars or euros in routing trucks, then that's more money you have to spend on the team. Race strategy I'll cover in a second, and of course you can see in race engineering how AI might help you understand options better. So this is really kind of a graphic of what a digital twin looks like. We start out with CFD, FEA, so aeroelasticity, vehicle dynamics. We create a physically informed surrogate model. We then go in and understand the error sources in all of these. That's the uncertainty quantification source. We have digital data sources we bring in, and we get a continuous data assimilation. That really becomes our digital twin. And we can then use this digital twin and an AI agent to adjust parameters at the track during testing, because now track testing is so limited that every lap, every corner has to be maximized. And so we can do this real time. And during breaks, lunch breaks, fuel changes, we can take the data, download it, pre-process it again, and then help us look at the design space once more. Overnight, if we have a second day of testing, we can process more and then be better informed for the next day. Of course, what can happen also is back at the factory, we can have a driver in the loop simulation that's running all these things. So the key thing is that every lap, we're getting the most data, the most accurate data, the best understanding that we can. This is the future. This is, there are opportunities now for small teams to shift the paradigm and become more efficient and better than large teams. In race strategy, there are so many factors, so many variables that go into this, and a human can't keep track of them. Now, you'll find that the pit boxes are full of people with gray hair and vast experiences making the decisions on when to pit and when to make changes. But what actually happens is that works great when things are going well, but when something unexpected happens, a flash weather change, unexpected tire degradation, that's when the AI agent can help the race engineer or the crew chief make better decisions. What the AI agent is not going to make the decisions. What that tool is going to do is going to suggest options to the human. The human is then going to make the best decisions. So AI is going to be a huge possibility for change in motorsports. It's going to be adopted. You're going to find that all the big teams are already going this way in Formula One, and in NASCAR, you're going to find this as an important thing. So, my concluding remarks are that motorsports is fueled by engineering, and engineering is fueled by education, which constantly evolves. I advise you, students, to maximize your time here. Learn as much as you can. It may be fun to go work on a race car on the weekends, or Formula SAE or Baja team, but don't let it distract you for your core mission. Your mission here is to put the tools in your toolbox that you will use later in your career. Remember that grades count. I was a hiring manager for a Formula One team. We would get thousands of resumes literally daily. And if you're getting that many resumes for internships, why wouldn't you pick all the ones with the 4.0s? I mean, why not start there? Now, certainly you're going to look and see if the person, the individual, has some type of motorsports background and experience. But remember, grades count. And again, if you want to work in Formula One, you have to remember that education is critically important. Now, you've already made a great step. You're at NC State. But finish strong. Get good grades. If you want to get a job in motorsports for a team, then yes, you need to have experience like Formula SA Baja, which Dr. Ecat has done an amazing job here. When I was here, the FSA team and the Baja team was in a faraway place. It was the Wild West. But he has done such an amazing job bringing and embracing those teams in and allowing students to have their lunch break or whatever, work on their projects, and then go back to their classroom. This is fantastic. This is a great institution. In my experience, Dr. Ecat, and what I've seen in the last few days, he's done just such an amazing job with this department. This department is strong and positioned for the future. You're going to be so thankful that you finished your engineering career here. Now, just a couple other words about education. If you want to have a strong career, you've already picked undergraduate engineering. That is a springboard for the future. But I recommend that you think about continuing your education. Even if your goal is to maximize your earning potential in your lifetime, an undergraduate engineering degree coupled with an MBA is super strong, super strong. You're going to find that that's going to increase your lifetime earnings maybe 40%. A Master of Science degree is also going to help you, and oftentimes you can go to work in industry for a few years and have that degree paid for by your company. So it will increase your lifetime earnings. That master's degree is valuable. So continue your education through your lifetime. Keep up with the latest. My wife is a physician. She works till midnight every night reading medical journals. I stay up to date with all of the technologies. And I'm going to tell you that learning is a lifetime event. You really have to take care of it. So I ran a little bit over, but I'll be happy to take questions.
Thank you, Dr. Jenckes. I'm going to open it up for questions. I'm pretty sure a lot of questions here. Please raise your arm. I'll come by and give you the mic. We'll start with Dr. Jenckes. Yeah.
Thank you. This is great. It's a once in a while kind of seminar like this. My question, actually two questions. The first question is, from all your experience with racing car, do you feel anything that I need that data, I need that parameter, but I don't have the sensing capability yet, what that would be, if yes? The other question is, can the human-driven racing car beat the unmanned racing car?
Great questions. I'll answer the first question first. Very simply, if you can't measure it, you can't manage it, okay? So whatever sensor that you want, if you want to understand airspeed, yaw performance, engine performance, you have to have sensors that can give you that data, and that's critically important. So as sensor technology advances for any parameter, we get better information and we can make better decisions and better designs. I think that was your question. So yes, sensor development is absolutely hypercritical, and we're always working on it. A very simple example of that is when we go to the wind tunnel. In the past, there used to be a pressure scanner that would have long tubes of connecting the measuring device to the static pressure ports on, say, the floor. Well, today we have very micro scanners we can place right on the floor, which cuts out any time constant in that measurement or any issues that might happen just with a tube getting pinched. So that's an example of an advancement of technology. I actually have worked at Purdue. I'm a mentor for an autonomous karting program, which is trying to make a go-kart, an electric go-kart, run around the Purdue Grand Prix track. a karting track. And I work with a very advanced team called Code 19. They sponsor this project at Purdue, and Code 19 competes in the autonomous challenges. And right now, no, the drivers, the human drivers will outperform the AI driver. But in the future, that may change. What I think, though, is not so much what can AI do as an AI driver, but how could AI help a human driver perform better? I think that may be the most interesting question.
Howdy. I just wanted to ask, so you talked about how AI is becoming very consistently used in pit crew and off the track. Is it currently restricted as far as how much use it can be, or how many prompts or how much time can be used for AI, and do you expect it to?
The first question is no, right now there are not, but yes, I expect in the future. The regulatory bodies are usually with very smart people, and they'll figure it out. Now, the regulatory agencies like the FIA have maybe 100 smart people, but when you take all the smart people at all the teams, they're in the thousands. So typically what you'll find is they set a set of rules, and then all the very creative engineers come up with solutions to meet the letter of the law, but work around it, and that's happened over and over again.
A quick announcement, there is going to be a reception after this and EB3, so you can continue talking to Dr. Jenckes over there, but we'll get one last question.
Hi, my name is Victoria. I thank you for the talk. It was very insightful. As you know, students looking to get into the motorsports industry, I'm really interested in knowing what was your hardest learned lesson that you kind of had to face when you were going through either your degree or working in the industry?
That's a great question. One thing is you have to understand that motorsports is not for everyone. The image of working in motorsports is often different than the reality. When I worked at Williams, it was often 12 to 14-hour days in the factory, and then 2 18-hour days in the wind tunnel. And I remember at lunch break on Sunday, my supervisor would say, well, we only have another half day to work this week. You know, I mean, it's extreme. It's very tough. It's very tough, and especially, you know, if you want to have any kind of life outside of it. In Formula One, young engineers that come out of uni, they're paid hardly anything at all, and so they're stacked up like cordwood in flats to make expenses. Often can't afford a car. You know, I mean, it's a very tough thing. And then you've got the issue of work permits. Now, there's a U.S. team down here in Concord, and if you can get to work with GM, then you can work with motorsports, but it's not the same as working for a team. You're going to find OEM work is not the same as a team. You know, a lot of people want to be at the sharp end of the stick. So having said that, how do you get in? You have to be relentless. You have to be absolutely driven and relentless. You have to look at all of the opportunities that you've got to start someplace. So it's tough to get, there's very few spots that open up at teams. So what you have to do is, when you're getting ready to graduate, is you have to apply for every possible job. And you have to realize that if you can't get a job working for a team, then can you get a job working for a supplier, like a braking company or a radiator supplier, heat exchangers? Get some experience in that fashion. That'll help you get the next job. You got to get the first job to get the next one. Some lucky people will get jobs with teams, but you know, you're talking about a fraction of 1% of all the students that are looking for these jobs. So also, if you're driven to have a job at a team, then make sure that if you're working for AP Brakes in Gastonia, and you're doing brake testing for motorsports, that's great, but make sure that on the weekend that you're volunteering for a truck team to gather data. And if you only want Formula One, don't be so closed-minded. You have to realize that NASCAR is a great engineering opportunity as well, and some time at NASCAR is as valuable as anything. You know, even when you start looking at Formula One jobs. Does that answer your question? So the biggest challenges I faced was being able to go back to school and still pay my bills at the same time. For the time that I was taking classes here, I took classes from great instructors like Dr. Zorowski, but the classes are hard, as you know, and especially the graduate classes. And so I was sleeping like 2 hours a day. That was the biggest challenge.
All right, I want to thank a few people. First of all, I want to thank Engineering Communications for setting this up. It's always good to have a well-organized event. I want to thank our staff. Several of staff helped us. Dr. Aishan, who is after retirement continuing to do this for us, running the Zorowski lecture. The family is here. Thank you again for continuing to support this and also coming to the lectures. And there are several of Dr. Zorowski's former students who are also here. So it's great to have them come every year and be part of this. So again, thank you again. And I want to thank our speaker one more time. I got a small little memorabilia here and also some MAE swag. So he can proudly display this on it.
Thank you. I would like at this point to say one concluding thing. Would all of the faculty, former faculty, and staff at NC State please stand up if you're able? Okay, these people do an amazing job. It's a tough job. Please give them a round of applause. Thank you all for what you do and what you have done. Thank you very much.
Jeff, you want to join?